This meeting is being recorded.
In section 3.3, we are going to take a look at how we can quantify acidity. So assign a numeric value to how strong an acid or base is. And you should recall from general chemistry how to determine if something is a strong or weak acid or base. That has to do with, or what we were told it has to do with, ionization. So the ionization of our acid or base, what percent of that we should say? So percent ionization. So for strong acids and bases, we generally would say that we have 100% ionization. And we qualify these strong compounds, acids and bases, and the pH or POH scale. So we use pH and POH for the strong. And then when we had weak acids or bases, we knew that they did not dissociate or ionize 100%. So we assigned those values on a different scale called the pKa or pKb scale for bases, based on a value called Ka, which we'll review is the weak acid dissociation constant. So we have weak acid dissociation constant. So we'll talk about how we can relate weak acid strength using the negative log of Ka or the pKa value. So quantitatively, we will measure using pKa, and in a subsequent video, we'll actually talk about how we could qualitatively compare structures to qualitatively measure acid strength or analyze acid strength. So let's take a look here. Quantitatively, again, we're going to use the Ka, the acid dissociation constant, which tells us how much is dissolved in water or how much ionizes when an acid is dissolved in water. So we have over here this generalized formula for weak acid dissociation in water. So we see we have our HA, our weak acid species, we add it to water, H2O, and then we generate the conjugate base, this anion over here, and hydronium. Right, so this is how we know that this is an acid. It has released a proton, it lost that H, and the water molecule, the base, picked it up. So when we look at the acid dissociation constant, we have this equilibrium established between the weak acid and water, and then the product side of the conjugate base and the hydronium ion. So this would be the full equilibrium expression for this reaction if we included water. But we know that the concentration of water will not change, so we can leave that out of our expression, and that's why we have this more simplified Ka expression shown here, where our two product concentrations, we have the hydronium concentration, again, brackets, those square brackets around each compound, that's what tells you that it's a concentration. So we have our hydronium times the concentration of our anion, and then we divide by the the original concentration of our acid before it ionized. So if the acid is strong, our Ka value will be bigger than 1. If it's smaller than 1, we know that it would be a weaker acid. So let's take a look at this expression again and how we can relate Ka and pKa to quantify acidity. So Ka in general ranges anywhere from very small numbers, 10 to the negative 50th power, or 10 to the 10th power, so very large numbers. So they can be challenging, right? If we have like 3.85 times 10 to the, I don't know, eighth power, that can be hard to envision this ionization and to then rank acids based on their Ka values. So what we do is we take the negative log of our Ka value and that will become a whole number digit. So, for example, if we have uh, the Ka value for acetic acid is approximately 1.8 times 10 to the negative fifth, when we take the negative log of that Ka, we would get a value about 4.74, right? So if we do this with all of our weak acids, we would have just a numeric value such as one coefficient followed by a couple decimal places. So it's a little easier to rank our acids, like so here. So we have this table that shows us some common compounds that we can rank according to their pKa values. So we have our very strong acid listed here with a very low pKa number. So this means the more negative our pKa value is, or the lower our pKa value is, the stronger our acid. And notice that will be paired with the weakest conjugate base. So we'll see this trend continue as our numbers increase. So the acid strength is going down as our numbers increase. So we see water here, or rather hydronium right here, as negative 1.74. So this is a good value to note. We're going to be talking about hydronium quite frequently. And the rest of this table is continued here. So you can see that these values, the pKa goes all the way up to 50. So these would be the weakest acids, these structures that we call alkanes here. And we have, everything in between. We have, here's water now here at 15.7. We know that water can be both an acid or a base, depending on its environment. So we'll see water used as both acids or bases. We have classes like alcohols, etc. So we'll get to know how we can compare the strengths of these acids using these pKa values. So let's take a look here and see if we can predict which direction equilibrium will favor. So again, they remind us here that the higher the pKa value, the weaker the acid. And the equilibrium will favor the weaker acid being formed and then the stronger acid. So let's see if that's the case here in this example. We have our two acids with their pKa values shown. We have water, the pKa is 15.7, and then we have this alcohol over here, which has a pKa of 18. So the higher the number, the weaker the acid. So this one is weaker. And that's what we see. We see that the equilibrium favors this direction to the right. And that's because the stronger acid would ionize in this situation, and the weaker would be favored. So this is the case. Equilibrium always favors, right? This is our take-home note here, always favors the weaker acid or base. The stronger will acid or base will ionize or dissociate. So in this next slide here, we can actually see by subtracting pKa values, we can see just how much stronger one acid is compared to another. So water is 15.7, our alkane over here, which is listed as a pKa of 50, would tell us that we would have at equilibrium about 10 to the 34 times more products than reactants. So this just shows you with those weaker acids or bases that you can have a much higher concentration at equilibrium. And down here they clarify that since this value is that high, this really is more like an irreversible reaction than an equilibrium. So we will continue with this section using some practice problems in the textbook.